To reinforce what you have learned so far with vector operations, let's solve now some sample problems. For our first problem, we're given two forces P and Q acting on bolt A, and we're going to determine their resultant. We're also given this figure in where the magnitude of the given forces are indicated as well as the angle of inclination. So we write first what is required, and that is the resultant. For our solution, let's solve first by using the parallelogram law. To draw our figure, let's idealize the bolt as a particle, and then let's draw the given forces and also the indicated angles. With this drawing, we can now draw the projected parallel lines so that we can form a parallelogram shape, and we can draw the diagonal that represents the resultant. Take note that by using parallelogram law, we draw the given forces connected tail to tail, and then we draw the resultant by connecting its tail with the tails of the given forces. With this drawing, we can apply trigonometry to solve the necessary dimensions. By alternating interior angle theorem, we know that this angle is equal to this angle, thus it is equal to 20 degrees. And to solve for this angle, we take note that this angle is just equal to the angle of force vector Q from the horizontal line. That means this angle is equal to 25 degrees plus 20 degrees, which is equal to 45 degrees. Before we can apply cosine law, we need the opposite angle of the resultant force. So let's represent this angle as angle alpha, and angle alpha and 45 degrees are both supplementary angles, which means that angle alpha plus 45 degrees is equal to 180 degrees. This gives us that alpha is equal to 135 degrees. With the value of alpha, we can now solve for the opposite angle of the resultant. Let's represent that by theta, and from the figure, theta is equal to alpha plus 20 degrees is equal to 135 degrees plus 20 degrees, and this gives us that theta is equal to 155 degrees. It will be better if, before applying cosine law, we highlight this triangle in which our solution will focus on, and then isolate that triangle from this drawing. So we draw now this new illustration in where theta is equal to 155 degrees. Take note that this dashed line in magnitude is just equivalent to force vector Q, which is 60 Newton. With this drawing, let's apply cosine law, in which the square of the resultant is equal to the sum of the square of the other two forces minus twice the product of the other two forces times cosine of the opposite angle of the resultant, which is theta. Since the values are already given except the resultant, let's substitute the values to solve for the resultant, and we obtain the magnitude of the resultant to be 97.73 Newton. If you will observe in some reference textbook that in mechanics, usually when they ask for the resultant, they're just referring to the magnitude. Example of that is usually in board exams, when they ask for the resultant force, they're asking only for the magnitude. But strictly speaking, and according to physics, when we are referring to a resultant force. It is a vector quantity described both magnitude by both magnitude and direction. So now let's solve for the direction of this resultant force by first setting a reference axis. Let's denote that as positive x-axis, and let's indicate the angle of inclination of the resultant with reference to our reference axis. Let's denote that as gamma. The value of gamma can only be obtained when we solve first with the interior angle, this interior angle represented by angle mu. So our target first is to solve for angle mu so that we'll be able to find the angle gamma. To solve for angle mu, we apply sine law, that is 60 Newton, which is this one, 60 newtons all over sine of its opposite angle, sine mu, is equal to the resultant all over sine of its opposite angle, represented by theta. This term is can be expressed as follows: 97.73 all over sine 155 degrees. With this term and this term, we can observe that mu is the only unknown variable, and we can solve for mu, and we get mu is equal to 15.04 degrees. With the value of mu, we can now solve for the angle gamma, which is equal to mu plus 20 degrees. This gives us angle gamma is equal to 34.05 degrees. With both magnitude and direction, we can therefore now have our final answer, that the resultant force is equal to 97.73 Newton, 34.05 degrees from positive x-axis. Before we proceed with the next method, kindly take note of this isolated figure, because this figure will just look like similar to the next method that we're going to discuss, or that we're going to use. So let's proceed. By triangle law, we first draw the given forces. Before drawing the given forces, let's take note of this illustration, or let's take note of the problem first, and then let's draw the given forces. So by triangle law, the forces are connected from head to tail, and that the resultant is drawn by connecting its tail with the tail of the first drawn vector, and then the arrowhead of the resultant intersecting with the arrowhead of the last drawn vector. So that's the process of triangle law. Next, we indicate the given angles, and this one looks similar to the previous method, in where the 60 Newton force with respect to the horizontal axis is inclined by 45 degrees. So we apply alternate interior angle theorem so that we can have this angle, and to get the interior angle that is opposite to the resultant, we first denote that angle to be alpha, and that take note that alpha and 45 degrees are supplementary angles. Therefore, alpha is equals to 135 degrees. So theta, the interior angle, or the angle opposite with the resultant, is equal to alpha plus 20 degrees, and we get theta is equal to 155 degrees. As you can observe, the process is almost similar, or the flow of our solution is almost similar with the previous method, because triangle law is just a special case of a parallelogram law. So we end up actually with the same procedure. We apply cosine law since we have now the opposite angle of the resultant. We substitute the given values and we get the magnitude of the resultant. Next is to define the direction of the resultant. We set first the reference axis. We denote this unknown angle as gamma. But before we get the value of gamma, we solve first the interior angle of this triangle represented by mu. This mu can be solved by applying sine law, and take note that gamma is equals to mu plus 20 degrees. So by sine law, 60 newtons all over sine mu is equal to r all over sine theta, the angle opposite with the resultant, or in other words, 97.73 all over sine 155 degrees. With this equation, we get the value of mu, 15.04 degrees, and this gives us the value of gamma by substituting to this equation that gamma is equal to 34.05 degrees. Thus, our resultant is equal to 97.73 Newton, 34.05 degrees from positive x-axis. As you can observe, the flow is almost similar and the only difference is the figure. Some students prefer parallelogram law because parallelogram law, by its drawing, is much more realistic, and it shows that the forces really acts on a particle. Other students prefer triangle law because triangle law, as you can observe, is cleaner when you draw the figure compared to the parallelogram law. You do not have so much dashed lines to draw. So it depends on your preference. So that's at least now you have seen the similarity between the parallelogram law and triangle law. There's some similarity, although the procedure of drawing the figure is somehow different. For our second problem, so we're given a barge pulled by two tugboats. If the resultant of the forces exerted by the tugboats is a 5,000-pound force directed along the axis of the barge, we are required to determine the tension in each of the ropes, given that alpha is 45 degrees. And the next question is that we need to find the value of alpha if the tension for the second rope should be minimized. Before we proceed with the solution, let's understand first this axis of the barge that the problem is referring to. If we actually observe the barge has two possible axes, that is horizontal axis and vertical axis. But when we imagine the situation of the problem, the two tugboats are pulling the barge. So this means that the resultant force is more inclined to act along the horizontal axis rather than on the vertical axis. Therefore, for this problem, the axis of the barge that this problem is referring to is horizontal axis. Let's write first what is required. So for the first question, let's denote the required tension as F sub 1 and F sub 2 if alpha is equal to 45 degrees. For the second question, we need to find alpha when F2 is minimum. For a solution, when solving the first question, we can actually use any of the two methods, either parallelogram or triangle law. But for this problem, let's choose one, since we have noticed before in the previous sample problems that we will still arrive with the same answer, either of the methods that you prefer to choose. So for this question, let's say we choose parallelogram law. So by parallelogram law, let's draw first the situation in the problem. So let's idealize the barge as a particle represented by point B. Let's say it's a point that is just enlarged. And then let's draw the given forces. So we have the resultant acting along the horizontal and also the inclination of f sub 1, which is 30 degrees. To draw f sub 2, we should draw it in such a way that we'll be able to form a parallelogram shape. So f sub 2 is this arrow defined by angle alpha. By applying our trigonometric knowledge or the alternate interior angle theorem, we know that this one is 30 degrees and this angle is alpha. These two angles are still unknown, so let's denote that with angle theta. We know both of these angles should be equal since the other two angles of these two triangles are also equal. For the first question, we know that alpha is equal to 45 degrees. When given the value of alpha, we will be able to find the value of theta since we know that the total of all the interior angles of a triangle must be equal to 180 degrees. So theta plus 45 degrees plus 30 degrees must be equal to 180 degrees, which gives us that theta is equal to 105 degrees. Now that we have theta, we can now apply sine law to solve for the value of f sub 1 and f sub 2. So let's start first with f sub 1. F sub 1 all over sine of its opposite angle, alpha, which is equal to 45 degrees, is equal to the value of the resultant all over sine of its opposite angle, which is theta, equal to 105 degrees. From this, we can get the value of f sub 1, which is equal to 3,660.25 pounds. We do the similar process with f sub 2. So the opposite angle of f sub 2 is 30 degrees and still equal to 5,000 all over sine 105 degrees. And we obtain the value of f sub 2, which is equal to 2,588.19 pounds. For the next question, we're going to find alpha when f2 is minimized. So when you recall your differential calculus, when we're going to minimize or maximize a variable, we should express that variable in terms of the target variable or unknown variable. Since the target variable is alpha, we will express f sub 2 in terms of alpha. The expression of f sub 2 will be derived by using sine law, as you can see here, where f sub 2 is all over sine 30 degrees is equal to the given resultant all over sine theta. So we don't know yet the value of theta for the second problem since we don't know the value of alpha. If theta is still unknown and we need this expression, we need sine law to express f sub 2 in terms of alpha, we need first to express theta in terms of alpha. To express theta in terms of alpha, we should use the similar process as we did here, that the sum of all interior angles of a triangle is equal to 180 degrees. Therefore, theta plus alpha plus 30 degrees is equal to 180 degrees. Thus, we can express theta in terms of alpha, such as this one. With this equation, let's apply sine law to express f sub 2 in terms of theta, and then later on express in terms of alpha. So f sub 2 all over sine 30 degrees is equal to 5000 all over sine theta. Then let's substitute this value of theta, or this expression of theta. And now we have f sub 2 all over sine 30 degrees is equal to 5000 over sine 150 degrees minus alpha. To simplify this equation and to remove the denominator, let's cross multiply so that we will have f sub 2 times sine 150 degrees minus alpha is equal to 5000 sine 30 degrees. Again, recalling with experiences in differentiating equations, when we are dealing with trigonometric functions, it is better to expand first the trigonometric functions before applying the differentiation process. So let's expand this one and simplify this constant. Now we have f sub 2 times this quantity. Take note that in trigonometry or in trigonometry, the expansion of sine of this trigonometric function, the pattern is sin, cos, cosine. And you just need to copy the angles and copy the sign. So it is sin, cos, cosine, copy the angles and copy the sign for the sine function. Then equal to the constant 2500. We can still further simplify this as follows, where sine 150 degrees is equal to 0.5 and cos 150 degrees is equal to negative square root of 3 over 2. And with this equation, we can now apply implicit differentiation. So we will differentiate f sub 2 with respect to alpha and set the derivative equal to 0 later on. So by product rule, we differentiate the first quantity and copy the second quantity, plus copy the first quantity and differentiate the second quantity, equals to 0 since it is constant. And we set the derivative equal to 0. That means that this one is equal to 0 times this quantity. Therefore, the whole term will become 0. This leaves us this equation, which is a much simpler equation. With this equation, let's copy that equation. You can notice that we can divide both sides with f sub 2 to get rid of this variable and to solve for alpha. So by dividing both sides with f sub 2, we now have this equation. And with this equation, since alpha is the only unknown variable, we can solve for alpha and obtain that alpha is equal to 60 degrees. So the answer for the second question is 60 degrees. So since we now have the alpha, just to visualize, we can redraw this figure so that it will be having the same condition as indicated, so that it will have the same condition as indicated in the second question. So let's redraw this figure. The second condition will look like this. So f sub 1 is still inclined with 30 degrees, and that for f sub 2 to be minimum, it should have the value of alpha is equal to 60 degrees. From our solution, we can conclude that in order for one of the forces to be minimum, it should act perpendicular to the other force. So the same goes with f sub 1. If f sub 1 is to be minimized, it should act perpendicular with f sub 2. Since, take note that 30 degrees and plus 60 degrees is 90 degrees. So when you encounter problems similar to this one, you may use that rule of thumb to simplify your solution or to quickly solve the problem. However, not however, it's still safe if you still have your differential calculus just in case you encounter a unique problem in where you need to minimize or maximize a certain variable. So that's the second problem. With all the concepts that we have reviewed and discussed, and also sample problems that we have solved, I hope you will go back to the objectives of this lecture just to see if you were able to understand the terms involved in mechanics and also the fundamental principles, and that you can recall the physics concepts that is essential for statics, that you also understand the concept of force and force system, that you're able to take note of the steps involved in vector operations, and that you can apply it to solve problems in order to get the resultant using either parallelogram or triangle rule. So this is the end of the topic. I hope you learned something new. Please stay safe and healthy always. Let's see you again in our next topic. God bless future engineers.